基本自己是快乐想要别在这儿。可咱这个是不是呢？说实话，那个纸的那个非常给做一个垫底啊，给它上回的滤镜是两个。我还是能还想把别人拿的那个without。就是没讲。有的是那个，这种下一个人就很傻。对啊，很多人我还是大家还是对不对？我还。For me, like, this is very yeah, you know, my problem is well, you have to. Yeah. It's on the you got the whole scene. 他的点非常能记录一个，但是我要是你关于，然后是哪？然后哦，那个I know I know。我给你这个是不是Right, and then just the whole because you want这只是完美的I like it. Yes. We're not ready for that. Yes. Like all of it. Yeah. Because I think that Marty said it's Marty. It's that guy. You may not think that sounds perfect. Yeah.
How are you guys? How's everybody doing? Okay. Recovered a little bit. A little bit. Yeah, please download this. There should be a Grasshopper file. And fine. In the folder for today. I hope it's there. It's called Grasshopper Introduction. It's this, okay? Just the you don't need all of that. You just need so this is something else. This is just something else. You just need this. Okay, just these two files. That's all. And the rest of it, you can have everything, but the rest, that's what I'm going to talk about today. we had a so we had this retreat I keep talking about where we talked about like the curriculum and what's necessary for you guys in the future of this world that we're entering in, and how we deal with all the crises and pedagogically and prepare you guys for the future. And I was in the computational section of that. We had a little meeting. And then we had big meetings. We had little meetings and big meetings. And I'm in the computational group of people, and we were obviously talking a lot about AI and what's necessary for you guys in the future. And Pan, who teaches here, who taught me a lot when I was a student. He works a lot on AI, and we were both sort of feeling that um, there used to be this very, very kind of known language of computational design. It's sort of been the language of a few basic principles that have been the language of how things were done in computers in relationship to architecture for about 30 years. And it is true that those tools are diversifying and changing. But his argument, his opinion is that actually the fundamental fluency in the same language of differential geometry and computational tools is necessary to meet the new AI tools in a kind of a comprehensive way. And also that while the current generation of tools is very text-based, that the next generation of tools is going to be less text-based to give you more control over things, and much more in a way like a smart version of Grasshopper. So this sort of made me feel like I should slow down a little bit and go through some of this Grasshopper stuff that I have found so incredibly useful in my career, like just actually very slowly. So that's what I plan to start doing today. I don't know how much we'll get through, but I would like you to follow along with me as much as possible. I think if I stand up in front of you and I just do things, it's going to be a waste of your time. I think some of you have familiarity with this stuff already, and then it'll be kind of boring for you. But most of you don't. And we'll get more complicated as we go. So I want to, next class, I want to actually go through some of my processes for how I deal with joints in modeling, in physical models. And that involves like a very basic, but slightly more complicated version of using these tools. And you can just use the scripts that I give you. They'll work just fine without any background knowledge. But it's been incredibly helpful for me to use this stuff in my career. It really has sped things up. So that's what I'm going to do. I'm going to go through it with you in detail over one or two or three classes, however long it takes. Okay. So the only other thing I wanted to say is just a little bit of a recap. I know I postponed the assignment. I know as you guys are doing those assignments, I want you to remember that the paradigms that I introduced in the first class for surface relationships, as you develop your details or as you think about how you want to develop your shape, I feel like it's important to respond to some degree to the paradigms that I put forth so that we have tools that will help you do that. And by the way, if you are doing these developable self-intersections, these are made of like this one or something like that is made of a single layer of skinny strip. I know Iman talked to you about at the very end of class about geodesic stripping, and I haven't talked to you about that yet. I would like to talk about it because it's a very nice introduction to differential geometry, but I think I want to do it after the grasshopper thing. But just so you know, we do have, as you're looking into this, we do have certain tools that will help you in that regard. For example, we have we have tools that will do like this sort of thing. This is like a long strip of joined surfaces, and this is a tool that is mapping like the geodesic tangent curve dynamically on it. So you can make sort of geodesic strips in that way. I don't think you need this yet for your material text. I think if you, the difference is if you're using a big sheet material and cutting it into a funny shape, you know, it unrolls into a funny shape. That is a different process than if you're using a linear strip that rolls up on itself. So we have these tools. We also have tools that will map skinny strips onto surfaces. So it's a new type of model. And we also have another tool here, which like if you have like something like this, which is a principal curvature panelization of a torus, of an asymmetrical torus. I have tools that will take a set of curves. Let me see if I can do this. They take a set of curves in one direction, and you put them in the in this way, and they take a set of curves in the other direction, and they weave them throughout each other so that we can make sort of spatial woven models like that. We can make models where we have two things weaving amongst them and predicting the length. So I don't think any of that is necessary yet. It requires the next step of the computational thing that I want to go through with you. But just so you know, if you're working with skinny material, I think we do have tools to support you rather than only the sheet material. Okay. So that is that's that. So and then as I was saying, I think just a reminder to go back to that lecture and look at the paradigms as you're thinking about what you're working in so that we can figure out a way. I think what they are really detailing vocabularies or things that your predecessors have done so that we know somewhat how the things are going to respond. And so in the weaving paradigm, there are really two kinds. One is this kind. These are strips that widen and shrink. They are made using the principal curvature. And the other kind, which we've never made models in, but which is the traditional kind, is where the strip is of a single width. And so that is a new kind, and we need the tools that I've just developed for that. So just a reminder, you know, these are the various paradigms, and I think you should be, you know, responding to and working within one of those particular paradigms. Okay, that's my sort of brief introduction. Okay, so now please download the Grasshopper introduction and the Grasshopper modeling file. Just a tiny bit of background. By the way, just so you know, I'm a competent, extremely competent, and also very amateur, like mathematician programmer. I entirely self-taught. So maybe some of you are not. Some of you have had courses in this. And if I say something that is wrong, I'm perfectly happy for you to interrupt me. Okay. Some of you have background in this. Few of you I know do. That's fine. Okay. But I think that in my old life, when I was a little boy, I studied like programming a lot in my spare time, and I forgot all of it by the time I got to graduate school. But I think that this one concept has been important to me in learning how to in kind of understanding what was going on. It's this idea of object-oriented programming. Most of the languages that we use, C++, Java, C#, Python, are what's called OOP languages. And those work around a particular kind of a concept that there are classes. You write what's called a class, and a class has properties which store data, and it has methods which act on the data, and it hides its internal functionality from everything else. So basically, you put some inputs in to a little black box, it stores data, it knows things about that data, and it knows how to operate on that data in a certain way. It does it hidden, pushes outputs out, and then another one does it. And you create what are called objects. So you write a class, and then when you're working, you create an instance of that class, an object. And an object is like, say, a class would be like class curve. A curve class knows certain things about what it means to be a curve. It knows how many points it has. It knows maybe how long it is. It knows how to calculate its, it knows, how many, what its endpoints are. It knows certain information, and it also knows how to calculate certain things about a curve. Like it knows how to calculate its tangent, or it knows how to calculate its curvature. And then when you make any curve, you're just making an instance of that curve, of curve class, so that it's an object, and it inherits all of the knowledge that curves have. So it inherits a curve's ability to store data, and it inherits a curve's ability to calculate certain things. And basically, you give your program some input data to an object which knows a bunch of things and knows how to do a bunch of stuff. It does some of those things in a hidden way. Then you pass that to another object which stores its own kinds of data, does other stuff on it. Then you pass it to another object, and then it gives you an output. More complicated structures are certainly possible, but this is the basic idea. And so Rhino is written this way. Rhino is written in C++, but the developer language is usually C#. And this is the API, which lists all the things that you can make in Rhino. You can go on there. There's the geometry, arcs, arc curves, Bezier curves, boxes, B-refs, and there's all sorts of things that it knows. Every curve knows certain things, and every curve, you don't have to go here, by the way. This isn't totally unnecessary for you to go here unless you're coding. But just to understand what's happening, a curve has certain information that it is aware of, and it has certain ways of calculating things on that information. And so I think actually when you're doing text-based programming, it gets much more complicated. But when you're doing Grasshopper, this is basically it. Visual programming, which is what it's called. There are many visual programming languages, and I think they will become much more common as we head into the future, are much more driven by this flow idea than by all the loops and conditionals of regular text-based programming. They're driven by this idea. Inputs act on the input, output act on the output, output act on the output, output act on the output. And every single version of the object stores its own data all over again. So when you pass a curve to another thing that works on the curve, it stores its own copy of the data. It's one of the reasons that Grasshopper is slow, because every single node stores its own internal duplicates of the data. Okay, so that is, I think, what has one of the just as important background information to have as you kind of come into these things. Okay, so this is, of course, the interface. You've all seen this a million times, but one thing that I think is useful is if you go Control-Alt-Click, it will show you where a node came from. So basically, in the file that I give you, the file that I gave you today is almost everything that I use on a daily basis. And if you want to find it, you can just click, you can Alt-Click on it, and it will show you where it is, okay? And then the other thing, I mean, many of you know this already, everything flows from left to right. And there are certain parts to a script, which is in Grasshopper, I think they're called parameters and components. That would be analogous to the properties and methods. A parameter stores data, a component executes some kind of a function. There are inputs and there are outputs. And really, Grasshopper, when it was first developed, used to be called modeling with history. So really, it is just a duplication of all the Rhino functionality in a more explicit way. So essentially, you're not really learning to code, just learning to do Rhino all over again from scratch. Okay? It's just a completely duplicate version of Rhino, except now all of the steps are recorded. So you cannot. So if you want to make a sphere, when you execute a command, you click somewhere and then you type in a radius. Same thing. You have to click somewhere. The point is the place that you would click. The radius is 100. And so you just have to look at the inputs, and those inputs basically match up with the steps you would take when you would execute a command. So you just have to relearn all the commands. And sometimes when you execute a command, you execute it very intuitively. You don't really know all the steps that you're doing. And now you have to know all the steps that you're doing, and you have to get the information that you would need to do it. And if you kind of mouse over one of the inputs, it will tell you what it's asking for. It's asking for the sphere's radius, and it'll have this little icon which tells you what kind of data it is asking for. And then, you bake things out, or you right-click on something. You right-click on a parameter. Parameters will either take information generated by Grasshopper, or they will take information from Rhino. Once you put something in a parameter, you basically, Rhino and Grasshopper are totally separate. Rhino has data. You take one of those data, load it into Grasshopper. Grasshopper does a bunch of shit. Then you export it back to Rhino. So the Rhino model is just there to load some information into the Grasshopper process. So you can right click on this and you can set one, or you can set multiple into the parameters. Okay. So that's basically how it works. So I do this long Rhino tutorial, which I've been doing for decades. And it's very similar to this, although this one tends to be, people tend to be, I've tried to do this many times. Sometimes it gets confusing. Please interrupt me. Please try to follow along. I will try to go slow. Okay. So in here, in the Rhino file that I give for my Rhino tutorial, there are just every command that I use. And this is sort of the same. These are, but not the more complicated things. This is all of everything in this file, just all of the nodes that I actually use. So if you alt click on one, alt control click, it'll show you what it is. Okay. So these are the parameters. There are sort of these number parameters, a Boolean, a true or false, an integer, obviously, this number, which corresponds to double numbers in computational language. It's a real number with decimal points, 0.11112 or whatever. And then a domain, which is a range of from something to something else, 0 to 100, 1 to 2 pi, a range. And then there are geometry parameters, and those are kind of split into two categories. There are the ones that are more mathematically defined, like points, vectors, planes, and lines. Those have a kind of a simple mathematical definition, and Grasshopper tends to be fast working with them because they don't require a lot of data. A point is really 3 numbers, an x, a y, and a z. A vector is also 3 numbers, an x, a y, and a z. A plane is 6 numbers. It's the normal and the location. And then there are more complex geometries that have kind of intrinsic definitions that are more intense. And those are curved surfaces. B-reps. A B-rep is the new word for a polysurface. A boundary representation. I don't know why. That's the new word for a polysurface. And then other things with kind of specific properties like curves and arcs these can be casted always into the main curve class, but they have their own kind of properties. Okay. Then there are inputs. So when you want to make something, you just double click and you just type it in. You say number, domain, There's a lot that come up though. So line, sometimes you get the wrong one. You have to know which one you're looking for. Brep, and they come up. Okay, and these are the things that you right click, set one brep, and load it from Rhino. And so these are the parameters, and they are the ones that get data from Rhino. And then there are other kinds of inputs that come directly from Grasshopper, and these are the only ones that I ever really use. There's Boolean values, true or falses. They turn things on and off. So if you type bool, you'll get this Boolean parameter, which holds a Boolean value, or the Boolean toggle, which can input a Boolean parameter. So if you double click on this, and then there's also buttons, which instantly turn on and off. And then there are over here, these are kind of the world reference coordinates. So the unit X, the unit Y, the unit Z, the unit XY plane, the unit XZ plane. I use these a lot because they're helpful shorthands. If you want to like move something vertically, you would need to get the world unit X. It sort of maps onto when you type into Rhino move vertical, you need a reference. And then those are just if you type unit X, unit Y, or world, I guess it's XY there, XY plane, XZ plane. Okay. And then there are the number inputs, which are typically in sliders. So if you type number slider or it's slider, I don't know. I don't usually access it that way. I usually just type a number like 10.00 will give me a number, or if I type an integer number like 25, it'll give me an integer slider. And if I right click on this and go edit, I can change the maximum to the minimum, and I can change whether it is a real number with decimal points or whether it is a integer without them. And I can also change the number of decimal points that it will store. And then finally, there is the panel, this thing here. And that thing is what I use to display information. It will tell you what's in a component. Here you can see that it is the unit Y vector. And it will also you can also disconnect it by holding control and dragging. And you can type things in here like 25.00, in which case it would function just as well as an integer. So whenever I don't understand what's going on in my script, I usually use this method of diagnosing. Okay, so you can connect them up like this. You can have a Boolean toggle connect to a Boolean, connect to a output parameter, and then if I click, you can see that it's changed. Okay, so they're all just storing duplicates of the same piece of data. And also, sometimes it will cast things automatically for me. Like if I draw a line in Rhino, and then I make a curve, and I put that line into the curve, because this is a linear element, it will let me cast that to a line, and it will also let me cast it to a vector. So sometimes that will not work. If it doesn't work, it will give you something red. And then if you look in this, you can see it's changing the data type as it goes along. This is a referenced line-like curve. Here's a line. Here's the vector that came out of the line. Some things you cannot do that with, and sometimes the casting is automatic. So this goes back to what I was saying before. A curve is a type of object of class curve. A line is a different type of object, and changing one into another is called casting. And Grasshopper has a lot of when you're writing programming, you cannot cast anything very easily. When you are doing Grasshopper, a lot of that functionality is already built into the program. If you want to make a domain, you would do domain. There are many kinds of domains. I want to do a 2D domain, which is this one. And then it asks me for a start and an end value. So I would type, 0.00, and I would type, 10.00, and I would put that in. And then if I look at the output, it will tell me is 0 to 10. Is the other kind of these domains tend to be very, very helpful. If I wanted to model something very basic, let's say like a sphere, I would start with something from Rhino. So I would say like, if I type sphere, there's the command for sphere. There are many different kinds. This is they correspond in many ways to the Rhino commands. This would be the sphere center point. That would be the sphere 4-point. They're very similar to the Rhino commands, although not identical. There, it's asking me for the radius, and it's asking me for the base, which is by default the world XY plane. But I could type point, and I could put a point, choose a point from Rhino, and then I could move that into the base. It will automatically cast it to be the horizontal plane. If I wanted to specify a plane, I would have to do something else. And then I type a radius like 100, and I put it in here, and it does that. Okay, so basically I need to look at what inputs it's asking me for, and I need to figure out ways of getting them. I could get them in some other way. I could build a point in some other way, or I could take a point from something else. Like, let's say I have this curve already in Rhino. I could do endpoints, take the start point, and then build the of that. So I need to find some way of getting the inputs for each of the command that I want to do. And the way that I set that up has a lot of influence on whether or not what I'm doing is at all useful for me. It tells me, it gives me control over what I am doing, basically how I set that up. So the rest of this now is divided into a variety of different sections: curves, surfaces, series and range, selecting, vectors, planes, transformations, and polysurfaces. These are all of the kind of basic commands that I execute on each of these different things. So I'm not going to get through all of this today, but very importantly, one other concept that is essential is, I think, thinking about parameters. Okay, so this word parametrization, or the word parameter, has many, many different definitions and used sort of interchangeably. But essentially, this idea is extremely important. A surface is actually a map from 2D to 3D space. Okay, this is one of the most, I don't know how many of you are familiar with this idea. One of the most important ideas in the world, that this is a space that is two-dimensional, and this is a space that is three-dimensional, and the surface is a two-dimensional thing in a three-dimensional world. And its equation is a map from its 2D universe into its 3D. One of the most foundational ideas. This is the notation. Surface is a map from a region U within R2, that's the 2D space of real numbers, into R3, it's the space of 3D real numbers. You don't need to know that, but it pops up in every paper. It means nothing. It's just a fancy way of saying this surface is mapped from 2D into 3D. And so when you when you find a point in a, when you try to find a point on the 3D surface, you need 2D coordinates to find a point on the 3D surface. So that is what a parametric equation is, okay? It is a map from 2D onto 3D. It is a way of mapping information. The U and V coordinates are 2D coordinates mapped into 3 coordinates in space like this. So when you are U and a V, U and V are the parameters of the surface. And this is a parametrization of a surface. U and V are 2D coordinates that give you a position in 3D space through this function. Okay, I don't know if that doesn't make sense. It's fine. But it's it's very important, and we return to it again and again and again. This is the fundamental idea. U and V are coordinates in the 2D universe of the surface. And then the surface is embedded in a 3D universe. And the same is true for curves. Curves are a map from a 1D universe into a 3D universe. So curves only have one parameter. Instead of U and V, they have T. And T has a domain. It includes some set of numbers along the number line. And that is mapped into 3D space. So if you want to know the position along a curve, you just need one number, P, the parameter, to find a position. So this is a parametric equation for a curve. It is based on one parameter, P, rather than 2 parameters, U and V. So this is what's called a parametrization of the curve. There are a bunch of little numbers along the curve that designate its position. And usually those numbers are totally random. They have absolutely nothing to do with anything. I don't know where they come from. They're just little addresses. And of course they go up. So this one goes from, it goes from, where's the smallest one? 103 to 332 or something. That's the address signature of the curve. Those are the T's. They're not for any reason. They just are there. But you can reparametrize a curve where the domain is 95 to 470. Then when you reparametrize the curve, you can right-click and go reparametrize, and that will change the domain always from 0 to 1. So then you can find a point along the curve using a T parameter to anywhere from 0 to 1, we'll go from the start of the curve to the end of it. So basically it's, inside of the curve just thinks of itself as a long straight line. But we know that it's something else because we're looking at it in a different way. And these T parameters tell you that. Does that nonsense or is that okay? Yeah. It will not show the number. I wrote the numbers on this slide. It will not show the numbers. It's very, very useful. So one of the things that is weird about Grasshopper is you kind of have to learn some funny things that don't seem that useful. But if I take a curve, okay, let's just do this. I go curve, set one curve, and then the thing I always do is evaluate curve. And this will take the curve and it will take a parameter. So let's put a parameter in here. Let's put 1.00 and let's drag that here. This is going to now give me a point and a tangent along the curve. This is almost always the first thing I do. But if I drag this slider, it is not going to look, it didn't get to the end of the curve. It went from here to some random point. And that's because the addresses of the curve if I were to type domain and look at it in a parameter, it's from 0 to 1.5. If I click reparameterize, now it's from 0 to 1, and this will go along the entire curve. So if I wanted to make a sphere along this curve, I could give it that point, and I could give it a radius, and I could drag this along. Otherwise, I don't know what numbers to enter in order to find a particular position. So this reparameterization, by the way, it's slightly inconvenient because certain areas of the surface will, yes. Thank you. I just double click and I type. Please, it is, thank you. It is not humble, it is heroic because everyone needs you to ask the question. Nobody wants to, okay? So yeah, you just double click and you type a thing in, which is tantamount to in Rhino entering a command and letting it try to guess what you're trying to type. So it is completely analogous process. You right click on it and go edit, and then you can change the maximum, the minimum, the kind of number. N is an integer, R is a real number, and then also the number of digits is the number of decimal points that it will hold. If I were to type a bigger number, it will automatically try to guess what range of numbers I'm interested in. So this is the main idea. This idea of parameterization is the fundamental concept. And when you were working with parametric equations, that is what they were doing. They were mapping a certain domain of 2D space into 3D space, giving you a sort of a signature, an address signature on the 3D surface for all the points. Okay? And for curves, it's 1D. Okay? And so then this little thing, there's others that I use, okay? I use also this perp frame, which also takes a parameter. And the perp frame component gives me a little perpendicular plane to the curve. And there's also the curve frame component, which gives me a frame that is a little plane that is lying in the plane of the curve, like that. And then I will also often use this tangent. So if I want to draw a line that is tangent, the thing that I use is something, I always type SDL, which stands for start direction length. It's a way of drawing a line. The other way of drawing a line is you can do line, just the basic line makes a line between 2 points. This uses a direction and a length. And I will take the start point, take the tangent, and put also a number slider in. So let's say 100 into the length. And there, let's turn off this sphere. If I want to hide something, I can middle mouse click and put the little blindfold on. And then this now you can see is a tangent line to the curve. That is line SDL. It takes a vector, the direction, start, a point, and a length, a number. And it produces a line. And because the line was created, the tangent is being evaluated this curve evaluate component. It's quite it's tangent to the curve. Another thing I could do is I could divide the curve into a certain number of so let's clean this up a little bit. Could divide the curve into a certain number of points. That would be this divide curve. There's a bunch of them. Divide curve, divide distance, divide length. They have different things. Divide curve. If I mouse over these things, this takes it says takes a curve, takes a number of segments, and then this is often unnecessary. So I'm going to drag the curve in here, and you can see it created a bunch of points. And if I change that number, so let's make 25, it'll make more points. And then this gives me some different outputs. It gives me again the points, the tangents, and it also gives me the parameters. So if I look in those parameters, they will give me a long list. So there they are. 0, 0.08, 0.12. Okay. And so those, that is how I made that other diagram. I just took them from here and wrote them on there. And if you wanted, you could use all of these parameters to do one of these other components. So I could drag these parameters all over here into the curve frame, and it would do the same thing. Yes. Thank you. I just go delete. The delete key. Yes. Although, by the way, sometimes it breaks and it won't do it. And you can also, I think there's a delete button somewhere. Does somebody have it? I'm just doing delete. That's what I'm doing. I feel like there's a delete in the menu. Here it is, delete. You can delete that way too. Okay. So what's happening is that this is what's useful about Grasshopper is that rather than me having to execute the command 25 times, it runs this component on every single number that I give it simultaneously. Okay. So it does the same functionality that it did on one number, but it just does it on all. And this is what's called a list. So this is the hard part, is getting the lists to match up with each other. It's very confusing, causes things to crash because it's trying to do an operation 25 times. But basically, usually you will not just get a single number output, you will get a list. And the list is if you feed a list into the input from another component, it will do it all of those times. So this is taking one curve and 25 inputs, so it's going to give me 25 outputs. So if I had 3 curves and 25 inputs, it would give me 75 outputs. Okay, so it very rapidly scales up, and that is what can cause you to crash. Does anybody have questions about this? Yes.
What type? Look at anyone and what? How would you like describe your flow of thought to know like where to get to the fighting point and how to construct all the different operations and where each one?
I think it's the same, almost identical to how you know what you're going to do in a environment. It's just like you already know all the commands for Rhino. You just know what commands exist because you've been practicing with it for a while. And so like there's this, it's not like being a programmer, it's nothing like that. I just know what commands exist. I've used them many times. So like I know that if I want to model a line, I'm going to use a line SDL. It's just a command. SDL is the same thing that you would type in like CAD for line. Instead of typing line, I type SDL. I just know. In terms of knowing the data structure, the structure to produce something complicated, that is more interesting. At a basic level, it's just modeling, just trying to anticipate what you would do when you're modeling it by hand. You just have to know all the steps in advance. So like if you modeled something by hand, like you would just do the exact same thing, but it's like recorded and written out in this weird format. So like if I were to make a line, like sometimes like I'm either going to draw here and draw there, or I'm going to just drag it in a direction. So I know that like I'm like, it's the same as like, it's the same as if I were to click on a point and then drag and type a number. It's this way of entering a line is a point, a direction, and a number. So it's a different way of entering the same information. Then beyond that, I think there's and that's why by the way, when I was a student, I never used books. I only used it in practice because I needed to do things very quickly for competition. I needed to like model hundreds of railings for like a rendering model in a competition. And so like I just started very small, like I'm just gonna automate like all the mullions in this rendering. And then like over time, like it becomes very familiar. So like I think like if something is extremely laborious and kind of a basic modeling task, that's a good way to start. That's why what we're doing in this class with like modeling bolts on surfaces, I think is like much easier than trying to model a parametric building. Like that is much more elaborate. Then the other thing I would say is that there is a small aspect of Grasshopper that is not just modeling, that has to do a little bit with coding. And that there's something, I wish I had my pen, but we in the programming, you call it pseudocode. Like it's like a little algorithm of like what are the steps that I'm going to follow. So I could write that out, like first divide the line into points, then get the tangent from each point, then extend that, linearly by a certain number. That would be like the pseudocode version and that actually is the primary idea. So like the good part of computer programming is not the syntax. It's the intelligence of what steps you're going to actually follow, because many are much faster than others. And so like if you follow if you have a good series of steps, you might not know the command to put in, but like, you just ask your friends or you ask me.
How like let's say a problem it beats, like for example just now when there was a point it didn't go all the way because it didn't parameterize the operation. Like
Yeah.
how do you know like that is and how
Yeah, I mean that is like experience, but also it's because this parametrization idea is like a fundamental idea. I think it's the most important idea. Actually, one of the most important ideas in the world. This idea of taking that you can take a 2D space and look at it in 3D space. I think the idea that a surface is a 2D space is really important. It's a little abstract, but it's really important. This idea of thinking about the world as spaces rather than it's great because we're architects. So like, actually your spatial intuition applies to all sorts of weird scenarios because the world is made of spaces. And by the way, in AI, it is a multidimensional space. That is what it is. It's a vector space of many dimensions. And when it's trying to find an answer, it's wandering around in the space. It's path tracing in a many-dimensional space. This is a two-dimensional space or a one-dimensional space, and we live in a three-dimensional space. Yes.
When you're like unrolling a 3D space or a 3D like surface to 2D, but some of those spaces like overlap with each other, how do you like determine the UVs then? Because like a UV on one of the surfaces is technically the same as the other one, if you know what I mean. But
Yeah,
they're really
I mean, very interesting question. It's like, so, I mean, the fact that the thing overlaps itself when it unrolls doesn't, it's complicated, actually. So when you unroll a developable surface, that is a map that preserves length and preserves angle. It is truly the same length and the same distance and the same angle that you would travel along the surface. If you were like an ant you have to think about it like you're an ant. It's like the world is just really skinny. It's like a super skinny world. Really, this is how mathematicians do it. It's a sort of a skinny world on the surface, and you're an ant. Okay? Like, and so what you know as an ant is what the surface knows. And the question is, how much can you know as an ant? And how much do you have to be outside to know it? And then, you know, it's true that like there's an abstraction there when it becomes truly 2D, but it's very not important to think about. You can mostly just imagine that you're an ant. Okay? And so when certain surfaces, the surfaces that unroll, that they preserve their size when they unroll, are the developable surfaces. Very rare developable surfaces. They preserve size when they are unroll. That is what it's called an isometric map. It is distance preserving when it unrolls. Most maps are not. Most maps stretch when they unroll. So that's what's happening. It's called an isometry. There's an isometry with the planar world when you can unroll something and distances preserved. Okay? And sometimes things truly self-intersect from the point of view of the ant. Like if the surface is like a Klein ball and it comes through around itself, from the point of view of the ant, it self-intersects. And other things just self-intersect because they flop on top of themselves when they unroll. That doesn't matter from the point of view of the ant, because in 3D space, it was not doing that. So the coordinates are still normal from the perspective of the ant. Like if you have like a cylinder, you know, a cylinder has a weird topology. You go around one direction, you just go endlessly. The other direction, you come around, you bump into yourself. Like that's what the ant knows. You know, and that's its topology. The topology is what the ant knows, and the geometry is what we know from the outside. The geometry is what it looks like. The topology is what you can know as an ant. So, like, you know, some things self-intersect topologically, and other things only self-intersect geometrically. Difference. Does that make sense?
Yeah.
Yeah. Okay. Great. So, back to this. Yeah. So this is the same command, line SDL. I can't help you with doing the algorithms, but you will get familiar with it just the way you're a master of Rhino, and some of you didn't even use it a couple of months ago. Same thing will happen again. Okay. Great. So what else is down here? I think that's it, except there are a few other divides. There's divide curve, divide. Oh, in terms of the things to know, I'm putting everything that I think is worth knowing in these files. So in terms of the numbers of commands and the number of the little widgets and buttons, most of them are unimportant. In a software is usually 99% of it is unimportant for very special cases. And most of it is like, most of the things that you repeat is like a very, very small subset of functionality. So like there's divide distance and there's divide length. Distance is equidistance. It's the straight line distance. Length is the length along the curve. And divide curve is a specific number. So if I were to divide length, it would ask me for a specific length, let's say like 15.0, and I'll get points that are 15 that are spaced 15 units apart, as opposed to a certain number of points. So that is what I do with curves. Okay, that is basically it. I divide them, I evaluate them, and I get these perpendicular or orthogonal frames. The plane is useful because certain commands take a plane, other commands take a point, other commands take a direction. And so you basically sample the curve for certain information that then you can use in other components. So that's what's here. Here is evaluate, divide, the curve frame, and the oh, I forgot one. There's a curvature. Curvature is what I was using before to get the osculating circles. So like this right here is the oscillating circle that I was talking about. Right? Okay, now there are surfaces. Okay, and surfaces are very similar. Although there is also surfaces take this surface thing. That is always one surface. If it's a joined surface, you have to use a polysurface. So, or what's called a B-rep. Okay. So if I put a surface in here, let's do set one surface. There it is. And then there's evaluate surface. And this is the same thing. So I can also reparameterize a surface. Okay, because the surface, unlike a curve, takes two coordinates, but it's the same thing. So it's asking for a point. It says a UV coordinate to evaluate. I have to say this is always very confusing for people. There are no 2D points in Grasshopper. So what we use is we use a vector. We just use a vector, and we ignore the Z component, and we just put numbers in the Y and X component. It's annoying. I wish it wasn't this way because we have to talk about vectors. And so if I put two numbers in here and then I drag this vector into the point, it will work. And the Z component is 0. So if you look at this in a little panel, it looks like this: 0, 1, 0. A vector, you remember from physics, a vector is like an arrow. In computers and in math, a vector is just a way of storing numbers. Just 3 numbers in 3D space or 2 numbers in 2D space. That's all it is, just a list of numbers packaged together. So this is how we're using it. And if you see, nothing's going to happen when I drag these around. Nothing is happening. And that's because I haven't reparameterized this surface. But if I right-click and reparameterize it, now you can see it's giving me the coordinate signature of the surface. So when I put bolts in surfaces, this is usually how I do it. And then it's giving me a bunch of information about the surface. It's giving me the 2 tangent directions, giving me the normal, it's giving me the frame, and it's giving me a point. So if I want to draw a line here, I can again do the line, the SDL. I can do from the point, the normal, and I can do a length. And there's a little doohickey sticking out of the surface that I can move around. Yes. The numbers are just the parameter. So they are the local coordinate space of the surface. They're its U and V domain. So because I went to reparameterize, they're from 0 and 1. It's 0 to 1, 0 to 1. If this was not reparameterized, they would be random things. I don't know. Let's see if I do a domain, if this will tell me the domain. I don't know whether that's the U or the V domain. It's just this. It's probably the U domain. It's just a random set of numbers. Like really has nothing to do with anything. It's just whatever was assigned when Rhino created it. They don't have to do with distance. I have no idea what they're just random. You can't rely on them. Maybe. Yeah, it could be. I have no idea why it's that way. It's not the length. It's not the length of the surface. If it's parameterized by length, that's what's called an arc length parameterization. Very great. But it's not that. Okay. So you could also yeah, so that's this. You can also divide surface, and then it will get you a bunch of them, just the same way we did before. I can make 100 of these. And then if I want all the little normals, I can make a like a fuzzy surface. Um, okay. And or I could take all these parameters, and if I want the curve frame, which I didn't get from this component did not just gave me the normal and the points, but it also gave me the parameter. So if I look at those parameters, you can see them, and I do not have this reparameterized, right? All I have is the original parameterization, and this is returning 0 to 267, 0 to 245, negative. It's just returning the parameters. If I go down this list, eventually these will start changing. There, you can see them all the parameters. And if I put those in this component, it'll evaluate at each one of them and give me these little local frames. Okay, and those frames are very helpful because let's say I wanted to model, little cubes or something all over the surface. Like if I were to do something like box, it wants a base plane. Many things take a plane, and then it takes a bunch of dimensions. So if I were to, I think these are all domains, so it's super annoying. Like, yeah, it's a domain. Oh no, it's just a number. Okay, so I could take this plane and put it in here, and then I can make these big. And you can see they're all oriented with the circle because the plane is the normal plane, is the tangent frame of the surface. So it's always called a frame. I don't know why. The tangent plane in this land is called the frame. The Frenet frame. Okay. So that is how that works. And so yeah, this was divide surface. And then if you want to do isocurves, you can do isocurve. And here, very annoying, it says UV point rather than point. Whoever wrote this was inconsistent, but it's asking for the same thing. It's asking for these UV points. So I could put in this vector, and because this isn't reparameterized, it's not giving me. So I can reparameterize this, and then you can see, let me turn all this off. You can see it's giving me the U and V isocurve. And if I mouse over the output here, it'll tell me what it is, I think, which is just a curve. Okay, so then I could take that curve and put it in its own parameter, and then I could evaluate the curve. Okay, so endless chains of data getting duplicated and passed to itself. Is that clear? And if I wanted to divide surface, I could get all of the isocurves that way. Okay. There are two other when I learned Grasshopper, every tutorial I went to started here with this stupid series and range, and I would always get bored. and decide to put it away and come back later. These are just ways of making lists of numbers. I don't know why you uh want them, but they're very useful actually. So if you type series, there aren't any others. These are them. Series and range. This is the way. There's no other way. So if you want a series of numbers, you need a start, a step, and a count. So you put like 0.0, 1.5, and 25. And that gives me 25 numbers from 0 to counting by 1.5. And one thing that I think is very worth noting is for some reason, computers always start counting from 0. They never start counting from 1. So if you have 25 numbers, the last one will always be called number 24 because 0 is always included. It can be very confusing and often cause you to lose track of your things. This is 25 numbers from 0 to 24. Okay. And then the other one is a range, and that takes a domain and a number of steps. So if I made a domain, which is what I did before, from let's say 0 to let's say 76.55. And then let's give it 25 steps. Now I have it just dividing down the domain into that many number of equal steps. And it's weird, it returns an extra number because it's dividing it into 25 parts rather than giving me 25 numbers. Okay, so this is useful because let's say I wanted all the isocurves on this surface. The other way of doing it with points was actually giving me overlapping isocurves because there were too many points, 2 points. Like if I have I need a pencil. If I have a surface and I have a point here and I get this isocurve and then I have a point here, I'm getting the same isocurve twice. So if I wanted to get all the isocurves, I could construct it this way. I could construct my own mapping of the surface using this range. I'm going to do a surface, set one surface, and then I'm going to do a vector, x, y, z. This is the same thing I did before. Whenever I need to construct a parameter, I use a vector. I always use vector x, y, z. I don't know, it just takes an x component, a y component, and a z component, and it builds a vector. The vectorness is not important. It's just a list of 3 numbers. So I'm going to put those into both the y and the z component, and I'm going to make this from 0 to 1. And now if we look at this, it is going to be returning a list of numbers where both the x and the y component are traveling from 0 to 1. And then if I do the isocurve, it will give me, and reparameterize this, it's going to give me all of those isocurves. So if I change this number, okay, that is because I'm constructing a list of parameters. Here I'm constructing 9 parameters, getting a set of numbers out of the range, and I'm using it twice for the x component and the y component to construct a vector. I think that's confusing, by the way. It's confusing to me when I say it, but I'm just showing you why you might want to create your own range of numbers. It's just an example. of creating your own range of numbers. I rarely access surface information this way. I'm just saying it as an example for how a range of numbers is sometimes used for a particular like other thing. Maybe a more salient example would be like if I divided the surface down and I wanted to make like every one of these normals like a different height, I might need a range of numbers in order to do that. But in order to do that, it would require using a bunch of extra components. So this is just a simple example with components that I've gone over already. Okay. Anybody questions about that? I think we only have 4 more minutes. So I think just to let you know, I think I probably will skip it right now, not do it right now. But I think the other thing that's important, okay, is to think a little bit about vector. There's a small amount of math that you have to remember. And it has to do with vectors. So I think I'll probably say it now, and then I'll say it again at the start of next class because it's important. And I think it bears repeating many times. Oops. I don't know if you guys remember your trigonometry, but basically this is trigonometry in a graph. The sine and the cosine function are really just a ratio of the sides of the right triangle taken from the Pythagorean theorem. It is just a function that prints out the ratio. That's what defines it. And so this, as you can see, the y is getting smaller as the x gets bigger. And here the y is getting bigger as the x gets smaller. And that's what makes the sinusoidal function when you plot x and y next. So it's all the Pythagorean theorem, x squared plus y squared equals r squared, the radius of the circle. And a scalar, what's called a scalar, is just a single number, this, and they can be plotted on the number line, anywhere on the number line. And a vector, what we learned about in physics, is a direction and a magnitude. And it has 2 components in 2D. 5 along the x, 2 along the y. And it has a magnitude which is calculated using the Pythagorean theorem. And you can plot a vector anywhere, and it is still the same vector. And vectors also exist in 3D. And then they have 3 components: an x component, a y component, and a z component. And their magnitude is again calculated by using the Pythagorean theorem twice. And when you unitize a vector, it makes its magnitude 1, and that is dividing each of the numbers by the magnitude of the original vector. And I'm going to end here. Vectors have many notations, and they are all the same thing. A vector is really just a list of numbers, and sometimes it's not a list of numbers. Sometimes it's a list of other things. But for our purposes, just a list of numbers. So they can be written horizontally like this. They can be written vertically, or they can be written as multiples of the unit vector. And this is just notation. It has nothing to do with math, just notation. So this is important. There is one thing that you need to remember from your education in order to start doing computational design, and it has to do with vector arithmetic. Okay, it's the only thing we have to remember. You can forget calculus, but vector arithmetic and trigonometry we have to remember. So I will go through again next class. I'll go through the dot product and the cross product and all that jazz because we have to remember it. Unfortunately, the only bit that we must remember. Actually, the rest of it you can forget. I don't know why they make you take calculus. It's a great idea, calculus, but it's only useful as an idea. We don't actually do it ever. It's a great idea. We don't do it. But we do vector arithmetic. Okay, so we'll go through that next class, and we'll keep going with this. Okay.